Okay, so we want to do this problem. I first want to give a little information about the eigenvalues for phi here. Now, I say here you may assume that all eigenvalues are positive. I'm not going to assume that. So I want to show that. Now, you don't have to do that, but I do want to show that. And to do that, I'm going to use the Rayleigh quotient again. So I'm going to come back here. This is the Rayleigh quotient here. Okay, so first we show that eigenvalues are positive, which isn't required. Okay. So R of u, so we're going to look at the smallest eigenvalue. So I want to show that lambda 1 is positive. The smallest eigenvalue is positive. All eigenvalues are positive. Smallest here, smallest can kind of be ambiguous if there's negatives, but it means the most negative or the close, whatever. Okay, this eigenvalue is less than all of the others. Okay, so this is equal. So lambda 1, let me just write it like this. Whoops. Lambda 1 is equal to the Rayleigh quotient here, and there's going to be things that I need to change here. I need to put this actually in the solution thing. Okay. All right, so P is equal to 1, so we're just going to have that. We're going from 0 to 1. So this is going to be 0. This is going to be 1. That's 1. Q is equal to 0, so this term here just completely goes away. So this is what we're left with. And then we divide by this. Okay. We want to know the sign of this. Okay, and actually we're just going to do this generically for all eigenvalues. Okay, so now let's look to see what we have. Okay, so we have what's going on here. We want to know the sign of this, so only the numerator is relevant. Okay, because the denominator is always positive, and sigma is equal to 1. The denominator is always positive, so we don't care about what the denominator is. For this problem, no matter what the denominator is, it's positive, so that's not going to change the overall sign. Okay, the numerator. So what's the numerator going to be? Well, phi of 0 is 0, so we only have this top boundary term. So the numerator is going to be minus phi of 1, phi prime of 1. Because if you plug in 1, you get phi of 1, phi prime of 1, plus the integral 0 to 1 phi prime squared dx. But notice what's going to happen here. We know that phi of 1 plus phi prime of 1 is equal to 0. So in other words, phi of 1 is equal to minus phi prime of 1. So this is minus, this is minus, actually, let me do it the other way around. Phi prime is minus phi. So we're going to have this times minus that. Whoops, what the heck did I just do? Did I just zoom in or something? Then plus the integral. I think I just zoomed out too much. I'm probably going to need to adjust this a little bit. Well, the minus signs, those minus signs cancel. and we get this square, and then plus this. Now, this definitely shows it's non-negative because this is non-negative and that's non-negative. So this is clearly non-negative since it is a sum of squares. Is it positive though? What if phi of 1 is equal to 0? And what if phi prime is equal to 0? So there's several different ways we can argue that this has to be positive. Okay. Here's how I'm going to argue that this actually has to be greater than this actually has to be greater than 0. There's several ways to do this. If it is 0, then this is identically equal to 0. The derivative is identically equal to 0, so that if the derivative of a function is identically equal to 0, it just means it's equal to some constant. Okay, the boundary condition at 0 gives 0 is equal to phi of 0, and well, if phi is constant, that's just equal to c, so c equals 0, and the eigenfunction, is equivalent to 0. Eigenfunctions are never allowed to be the identically equal to 0 function, so v of x is equivalently equal to 0, which is not allowed. So it is positive. Next, now this is the first part of what you actually had to do, because I told you you could assume they're positive, but this is one way to show that they are positive. Okay, so next what I want to do is I want to get an algebraic equation for the eigenvalue. So this is very similar to a question from homework 10, where I ask you to get an algebraic equation that the eigenvalue satisfy. Okay, so next, since lambda is greater than 0, this means that, actually let me do this as in a line. This means that phi of x is equal to a cosine square root of lambda x plus b sine square root of lambda x. Okay, and we also need to know the derivative for the boundary condition, so I'm going to put the derivative here. Whoops. We'll see why I'm not going to do that. That's going to be too much work. Okay. The boundary condition at 0. Well, what's going to happen if you plug in x is equal to 0? This term goes away, and you're just left with that term. In fact, you're just left with a implies a equals 0. So this, we're just left with the sine term, and now I'll do the derivative. This is equal to square root lambda b cosine square root lambda x. The condition at 1 says, that 0 is equal to phi of 1 plus phi of x, so it's going to be b. Well, I divide both sides by b because b can't be equal to 0, so it's going to be this sine of square root lambda plus this plus that. Or, okay, so if we solve this, if we move this sine to one side and divide by cosine If we move the sine to one side and divide by cosine, we get, there's going to be a problem here, isn't it? We're going to get, the square root of lambda is going to be equal to minus sine over cosine, so minus tangent square root lambda. Now this is an algebraic equation in the sense that it's not a differential equation. This is an algebraic equation that lambda satisfies. Okay, so what did I do wrong here? Got that wrong. Nope, got that wrong and got that wrong. Okay, I thought that caused me some problems. Too much copying and pasting. Okay, well, so now, so this is just one way to do this. By the way, this is just one way to solve the entire problem, right? There's other ways you could solve this that don't involve getting an algebraic equation. This is just the way that I thought to do it. So now we want to solve this equation. Well, how can we solve, like, what are different ways that we're going to be able to solve this equation? Well, we could do numerically. We could try that. There's a number of different numerical, like, non-graphical numerical methods that we're going to use. But that's not what I'm going to do. I'm going to do this. I'm going to say minus tangent square root x, and I'm going to graph. Wait, what's this problem here? Oh. Minus tangent square root x, and then I'm going to graph square root x. And whenever there are intersections, now there's an intersection here, but we know lambda has to be positive. At each of these intersections, that's going to be where there is an eigenvalue. So this eigenvalue looks like x is equal to about 4.1, one where x is equal to about 24.14, and one where x is equal to 63.66. We're going to come here. We're going to rename this to homework 9. I think I will do G3 to keep the thing going. All right. So I'm going to do some mini pages here. And I'm going to have one of my favorite things to do equals 0.484. Okay. All right. Oh, it's supposed to be like this. Okay, and so now I'm going to put the graph here. And I want the image to be roughly 0.9 of the line width. Okay, and it's going to be figs, figs, homework 9, and I want graph 3. Okay, so to the left is a graph. The eigenvalues are positive. Are the x values of the positive x values are the x values are the positive, or how do I want to say this? The x values, the eigenvalues are the x values where the curves intersect, but only the positive intersections. These are about, what was it again? This here is 4.12. 4.12. 24.14. 24.14. And 63.66 and 63.66. Okay, something has gone wrong here. Sorry about that. Why is this? Okay, what? Oh, because I don't do this. Hold on. Okay, sorry. I'm having all sorts of problems here. I don't know what I was doing wrong, or I did several things wrong. I don't know why I get it wrong every time I try to do that. And when I do it so often, it's kind of embarrassing. Okay, so this is it. 4.12, 24.14, and 63.66. Okay, that is it for this homework assignment.